Hello everyone. In this video lesson we are going to do the following. We are going to revisit the skills needed to be successful in our unit exam on behavior of matter. So we are going to go over a practice unit exam, and this is it right here and here, 20 questions. It's going to take probably 3 videos to do it. This is the first of the 3. Here we go. This question reads, which sample of CO2 has a definite shape, definite, so it's confined, we know what it is, it's a definite shape and a definite volume. To assist with this, take a look at this picture. So here we have our solid phase, right here, our liquid phase, and our gas phase. With the gas phase, well, if these particles are not in a container that's sealed, they will expand as much as space allows. If it is contained, then it will have a definite shape in a sense, but the particles are moving around. It's considered that the shape is endless. It is not a definite shape. In fact, it's not even a definite volume if we take the lid off here. They will expand indefinitely. A liquid. Well, liquid, the particles move about each other, changing positions constantly. Therefore, they cannot have a definite shape. They do, however, have a definite volume. Here it's described as a fixed volume. Now, solid, on the other hand, the shape is definite. It's not going to change. And the volume, that too will not change. Best answer for this one is, let's see, definite shape, definite volume, choice 4. In this question, it says 2 basic properties of the gas phase are. Let's revisit the same picture. Okay. And it's asking you to focus on the gas phase. So once again, a gas phase. Does it have a definite shape? Absolutely not. Definite shape. 1 and 2 cannot be choices. Does it have no definite shape? Yes. Does it have a definite volume? No, only if it's in a container. So, best answer here, choice 4. This question reads, 2 samples of gold that have different temperatures are placed in contact with one another. They are touching. Heat will flow spontaneously. That means by itself, without being coaxed or convinced to do so. It will happen spontaneously from a sample of gold at 60 degrees Celsius to a sample of gold that has a temperature of, well, this diagram may assist you. Let's make this bigger. There we go. And this picture is attempting to share with you that higher temperatures will almost leak into an area that has a lower temperature. So heat will flow from an area that's higher temperature to lower temperature. After inspection of these questions, which one of these has a lower temperature than the 60 degrees? Well, not 60, not 70, not 80. The only choice available that is lower is choice 1. Question number 4. Which term is defined as a measure of average kinetic energy of the particles in a sample of matter? Well, kinetic energy. Kinetic energy is the energy of movement. Let me straighten this out. This picture on the left, yes, the particles are displayed as being in movement, as in, the particles are moving. On the right, they are moving, but they are moving faster. And in moving faster, we're going to have a higher temperature. So that actually then relates to this picture here. And you move it. It's not letting me move it. There we go. And here are our 3 different varieties of measuring temperature. Kelvin, which is the most common used in chemistry. Celsius, which is also very common in chemistry. And Fahrenheit, not so much. But this is a measurement and our purest definition of temperature. So once again, average kinetic energy of particles relates to their movement, which relates directly to their temperature. In fact, they define each other. Question 5. Which change results in a release of energy? A release of energy. Let's take a look. Here are our states of matter. And in these states of matter we have solid, let me grab the pen, solid, liquid, and gas. Which one of these has to happen? Or, shall I say, let's apply these choices. The melting of water that's solid. So in order to go from solid to liquid, are we going to release energy or do we have to gain energy in order to make those particles move faster? It's a gain. So we are not releasing energy here. Number 2, the boiling of H2O. Boiling. We're going to be going from a liquid to a gas. Once again, you have to input energy. That's endothermic. Could not be number 2. The evaporation of H2O liquid. Once again, we're going from a liquid to a gas. Have to add energy. And 4, the condensation of H2O gas, which is when the gas becomes a liquid. In order for that to happen, these particles here as a gas must lose energy to make them go closer together. The answer for this must be choice 4, but let me also put on the screen and pause it to look at it. This diagram right here, which also defines it for you. So again, pause it, take a look at this diagram to help you understand the concept better. So here is question 6, which reads, which phase change is an exothermic process? Now, if need be, go back to the previous slide, take a look at my explanations for the previous question, but let's take a look at this diagram this time. And we're looking for exothermic, something that is now giving off energy in order to be achieved. So, in order to go from, well, choice 1 says a solid to a gas, going from a solid all the way to a gas. Endothermic or exothermic? That one's endothermic. We must put energy into the system to go from a solid to a gas. Number 1 is out. From a gas to a liquid. So we're going from a gas down to a liquid. Particles getting closer together. What will happen? Yes, energy will be released. 2 looks good. Let's look at 3 and 4. 3, going from a solid to a liquid. Solid to a liquid. Once again, energy must be put into the system to loosen up the particles. That too would be endothermic. And liquid to a gas, liquid to a gas. Hey, there's a theme here. 3 of them were going in this direction. One of these things is not like the other. One of these things does not belong. Choice. What was it again? From a solid to liquid? No. Gas to liquid? Gas to liquid? Yep, it was choice 2. Question 7. The kinetic molecular theory assumes that the particles of an ideal gas, or which one of these occurs. Let me show you the 4 assumptions for an ideal gas. Pause it, take a look at these, and then I'll disclose the answer in just a moment. All right, ladies and gentlemen, when you take a look at this, what matches? Particles are in random straight line motion. Number 1 matches. Let's take a look at the others though. Why are they wrong? Are arranged in a regular geometric pattern. That relates to solids.
Hey, have a nice vacation, babe.
Thank you, you too. Number 3, why is that wrong? Have strong attractive forces between them. Strong attractive forces. Once again, we'd be talking about solids. Liquids too have attractive forces, but not so much as solids. And lastly, have collisions that result in a system losing energy? Law of conservation of energy says we do not lose energy. Okay. Now that's for an ideal gas. No gas is ideal. Gases are really described as real gases, but we do have conditions you'll see in a question later.
Colonel Gully to the main, First Sergeant Woods, contact the main office. Thank you.
So we do have conditions that make real gases, those are the gases that truly exist, behave more like an ideal gas. You'll see those later, once again. Okay, and here is that question. Under which conditions of temperature and pressure does carbon dioxide gas behave most like an ideal gas? So what will make those particles spread out as far as they can, maybe even move faster and behave more like an ideal gas, losing their ability to attract one another? Well, if need be, pause this, take a look at these assumptions, and see if you can figure it out. I'll get back to you in a moment. All right, let's take a look at the first one. Low temperature. Low temperature. What would happen to particles under low temperature? Would they get further apart or closer together? Low temperature. They get closer together. Can't be number one. Again, low temperature. That choice must be excluded. So high temperature, and the question now is under low pressure or high pressure. First, let's discuss high pressure. High pressure. What would that do to the particles? Push them further apart or closer together? It would push them closer together. It cannot be four. So if a condition of high pressure pushes them closer together, low pressure must bring them further apart. Choice 3.